Good afternoon, everybody. My name is Sara Zullino, and together with Dario Longo, are running the Demonstrator D5. The title of my presentation is XNAT-PIC, expanding XNAT for image archiving and processing to preclinical imaging centers. So this is the agenda of my presentation. So first I'm going to describe what platforms are available for medical imaging. Then I'm going to tell you about what's behind the scenes of our preclinical imaging facility, what are the challenges we daily face, and what is the approach we are going to use to address these challenges. After describing the scope of this demonstrator, I'm going to show you the project achievements, in particular our application named XNAT-PIC that comprises a series of tools. An image converter from raw images to DICOM, a set of custom variables in XNAT by which you can extend an existing data type, an uploader to import multimodal large-scale image datasets, and a set of pipelines to process preclinical magnetic resonance images. There are several medical imaging platforms available on the market. The majority of them, such as XNAT, NORA, Chat, is devoted to clinical imaging. The aim is to help clinicians and researchers to perform their tasks by managing, visualizing, and processing, in some cases, their images. Very few platforms are intended for preclinical imaging, at least one to our knowledge, that is the small animal Chat that offers a paid service. Here we are with a very big question. What are the major bottlenecks in terms of dealing with image data for users in our imaging facility? Urgent challenges to be addressed for preclinical imaging facilities are related to collect, process, and reuse medical imaging data. In particular, we have different study protocols involving groups, time points, experimental procedures. Then we have several imaging instrumentations along with different imaging modalities, resulting in poorly organized data distributed over multiple sources. We have to deal with raw images specific for each imaging modality. And in addition to that, different techniques within the same imaging modality. We have a variety of users, such as master students, PhD students that need to be trained. This can result in data displaced over multiple personal desktops and therefore inaccessible. We have several processing tools, and this is the most delicate part, especially in the field of preclinical imaging. Image analysis is usually performed by in-house scripts based, for instance, on Python, which is free, or MATLAB that comes with a license. We have to deal with different output formats generated from processing, and of course, different parametric images. And so we have problems to maintain consistency among different studies or within the same study. So we need to track all the scripts and the tool we used for the analysis. What solution do we use in our facility about dealing with image data? Our approach is based on XNAT. XNAT stands for Extensible Neuroimaging Archive Toolkit and was developed by the Neuroinformatics Research Group at Washington University in 2007. It's an extensible, free and open source imaging informatics platform devoted to imaging-based research. XNAT can support our data management and processing needs in a number of ways. In XNAT, you can upload data, as XNAT supports a wide variety of medical imaging modalities, such as magnetic resonance imaging, PET, CT, ultrasound being the most popular. We have shaped the XNAT data structure to match the protocol used in our preclinical studies. XNAT includes an online image viewer that supports DICOM format with the possibility to install a specific plugin, a specific viewer for annotating images and drawing a region of interest. All data stored in XNAT is associated with a user-defined project. So basically, users are given access to data on a project-by-project basis. And importantly, XNAT comes with a pipeline engine that we have used to execute our pre-existing processing tools. The aim of our demonstrator was to develop a user-friendly, customizable workflow to upload preclinical image datasets, including several imaging modalities, to an XNAT-based archive system, and provide analysis tools for automated image processing and quantitative analysis. What has been achieved? We have developed a Python tool to convert raw magnetic resonance image data from Bruker Paravision to DICOM standard. We have developed a Python tool to upload multiple imaging datasets to XNAT with a dedicated data organization, and a suite of pipelines to process different types of magnetic resonance images and extraction of mean values from user-defined region of interest. Our project has been named XNAT-PIC, that stands for XNAT for Preclinical Imaging Centers, and consists of a set of tools built in Python based on this workflow. We have an XNAT-PIC uploader to import large multimodal imaging studies in DICOM standard to XNAT, MRI to DICOM, which is a Bruker Paravision to DICOM standard converter, XNAT-PIC pipelines for image processing based on tailor-made Python or MATLAB scripts. Basically, you can upload your DICOM images directly to XNAT, and then they will be archived as XNAT scans, or if you have raw data in proprietary format, you can first convert them and then proceed with the uploading. Once the data are in place, you can process them directly on XNAT using our processing scripts that relies on the XNAT pipeline engine, and upload the results back to XNAT. Since preclinical imaging equipment usually does not match any specific standards regarding data storage, and each vendor adopts a proprietary format for its data, we have developed a tool for converting raw magnetic resonance images to DICOM, which is the internationally acknowledged standard for biomedical imaging. MRI to DICOM is an open source image converter from Paravision to DICOM built in Python. The converter has been designed and tests on different versions of Paravision. How does it work? MRI to DICOM accesses the raw Paravision data structure, deciphers the binary file containing the image, and parses the acquisition parameters stored in different files into Python dictionaries. And lastly, it saves all the relevant information into the DICOM header and attributes. In particular, regarding the DICOM attributes, to deal with a new emerging magnetic resonance imaging technique named chemical exchange saturation transfer, a novel set of terms has been developed by introducing private DICOM attributes specifically devoted to this modality. The CEST dictionary items have been added to the standard DICOM dictionary provided by PyDICOM, which is the Python package to handle DICOM images. To avoid conflicts of private attributes coming from different implementers, a block has been reserved for this specific use. Preclinical studies, preclinical investigations may cover a wide variability of studies addressing specific scientific questions. Therefore, the data organization is usually tailored to the particular study of interest and needs to be adapted to the XNAT hierarchy. Here we have a schematic representation about our data organization in longitudinal studies. So, for instance, group is referred to the treatment administration and can have two possible values, treated or untreated, that stands for the control group. And then we have several time points that are related to the longitudinal examinations, for instance, T0 before, T1 and T2 after a treatment. And there is also dose, which is referred to drug dosage in therapeutic treatment investigations. On the right, you can see how how our data organization reflects the study protocol. XNAT is currently designed to upload 1 patient per time. So XNAT-PIC uploader has been configured to upload large image datasets or entire project of different modalities. When XNAT-PIC is launched, user can convert the raw image data or upload DICOM images to XNAT. It requires the XNAT web address and the login credentials, and then the users can create a new project or select an existing one among the list in the drop-down menu. Then they can browse to the directory of choice and type the number of custom variables. Regarding custom variables, to match our study protocols, I show you 2 slides before, and provide additional information about the image sessions, an XNAT feature to extend an existing data type through custom variables has been used. Beside the default variables, the XNAT users can specify an unlimited number of personalized variables. These custom variables can be reused within other projects, allowing for inter-project standardization. XNAT's core activity is the execution of pipelines. A pipeline is defined as a sequence of steps. Each step of the pipeline invokes an external application, a shell script, or an executable for processing the data. The pipeline is executed by the XNAT pipeline engine, which is a Java-based framework integrated within XNAT. The pipeline engine works with simple data flows and can perform computational tasks on project data step by step. Users can select a processing pipelines and a set of scans to be analyzed, set the input parameters if there are any, and submit to the pipeline. Pipelines in XNAT are defined by 3 XML documents. We have the pipeline descriptor, the resource descriptor, and the parameters descriptor, which is optional. XNAT is currently designed to run pipeline at subject level only. It means that you can analyze 1 patient per time, and this is of course not feasible if one needs to process an entire project or large image datasets. This is an example schema for processing diffusion-weighted imaging, but the same principles apply to other pipelines already available in XNAT. Bear in mind that this structure is flexible. It means that can be easily shaped to suit your needs, to suit your script. It's basically a matter of replacing the main processing script underneath. Pipeline can be executed on project level, either by selecting the scan of interest or letting the pipeline to automatically look for the DICOM attribute that specifies the acquisition protocol. Then the post-processed data are uploaded back to XNAT in the resource folder, available at each levels of the XNAT data structure and accessible by the user. The XNAT OHIF viewer plugin adds significant XNAT specific functionality, allowing you to open and view sessions, inspect your DICOM files, add annotations, and draw segmentation or region of interest in your scan, and save the data back to your XNAT project. Following the processing, and once the users has, for instance, drawn his region of interest, preclinical imaging users are usually interested in performing some simple statistics on the processed images. We have therefore developed a pipeline that applies a mask to a parametric map and then compute the mean value in the region of interest and then upload the results back to XNAT. This is a list of the pipelines already available in XNAT so far. We have pipeline to process T1 and T2 weighted imaging, diffusion weighted imaging to compute the mean value in a region of interest, and more pipeline to come, such as CEST magnetic resonance imaging processing pipelines. What will be the impact of our project on EOSC? Our demonstrator allows the preclinical imaging researchers to share and reuse image datasets, thus improving the reproducibility of the results of the analysis by using standardized processing pipelines and promoting open science by providing free access to the data and the tools we have developed. Indeed, you will find them available on GitHub very, very soon. You can find the links to the repository here. What about the future work and sustainability? We aim at integrating the image datasets stored in XNAT with controlled vocabulary and metadata. Then our demonstrator has been developed on local desktop environments, so we are planning to deploy our XNAT instance on a dedicated server for our facility. Some processing pipelines require MATLAB licensing, but we are planning to replace them with Python scripts. And there is a manuscript ready to be submitted for dissemination. XNAT-PIC is supported by the multimodal molecular imaging Italian node of the Eurobioimaging ERIC, and has already attracted interest from several European preclinical imaging centers. The interaction with the EOSC-Life technical experts was always useful and inspiring. We had very interesting and fruitful discussions with experts from Work Package 1, Work Package 2, Work Package 7 at different levels on different topics, from ontology mapping and metadata to cloud deployment. Overall, our experience as demonstrator in the EOSC-Life project was definitely positive. The interaction with work packages was efficient and productive. Based on our experience, the possibility to access to the EOSC-Life expertise, resources, and fundings shortened the time to carry out the project. We have definitely improved networking and established cooperation among research infrastructures and individuals, and moreover, attending training events and workshops was a great opportunity to build knowledge and share expertise. This brings me to the conclusion. So while the default XNAT installation provides a platform for securely hosting and processing clinical imaging studies, XNAT-PIC broadened its core functionalities in multiple ways to support preclinical imaging facilities. Indeed, XNAT-PIC consists of an MR image converter from proprietary file format to DICOM standard, an uploader to import full multimodal imaging studies to XNAT, a set of processing pipelines that can be easily tailored to your needs. Our aim was to overcome the current limitations that arise from the management and the storage of preclinical imagery, thereby facilitating the analysis of biomedical image data. We would like to thank all the people that have contributed to the realization of our demonstrator project from University of Torino and the EOSC-Life Consortium. A special thank to all the work package leaders for their incredible work. And of course, thank you for your attention. Please visit our CIM-XNAT instance available at cim-xnat.unito.it. And if you have any question, I will be glad to answer. Thank you.